Hi folks. Today we're going to start to look at applications of differential calculus, and the first one we'll take a look at is trying to find maximum and minimum points on a curve. Now for our algebra today we'll look at polynomials only, but let's start by investigating this super weird function that is drawn in front of us. And one thing I want to check out on this curve is where is it increasing? So I'm going to trace that in blue. There we go, it's increasing there. It's increasing over this region, and it's increasing here. Think about the slopes on all those increasing parts. The slopes everywhere where we have it in blue are positive. So if you're increasing on the original function, that is the same as having a slope, or an f prime, that is positive. Now, let's take a look at what's happening when it's decreasing. Here's a decreasing region. Here's another decreasing region, though, goes to a slope of 0 for just a second. There we've got decreasing. Everywhere that it's decreasing, it would have a slope that is negative. If we want to find max and min points, we care about where it changes from going to a positive slope, or increasing, to a negative slope, which is decreasing. And so let's just catalog those points. It happens right here, right here, right here, and it also happens around the asymptote. And there's something that all those places have in common. At those places there's either a slope that is 0 or horizontal, or there's a slope that is undefined, which is what's going on right here and at this discontinuity here. So let's catalog what we know so far. On a curve, if f prime is greater than 0, or f prime is positive, then f of x is increasing. If f prime is less than 0, or negative, then f is decreasing. And a max and min is going to be where it changes from either increasing to decreasing, or decreasing to increasing. If we read the next little part, it says a curve can only change from increasing to decreasing, or vice versa, by passing through a slope of either 0 or undefined. So as a result, we care a lot about the places where slope is either 0 or undefined. They're really the quick way for us to establish the most important points on the graph, the places where we might have a max or a min. And so we call those types of points critical values. A critical value is an x value that causes f prime to be 0 or undefined. Once we find out the critical values on some function, then we can make a sign diagram around them to help determine the behavior of f of x. And that means that we can more accurately draw some higher order polynomials. We're going to start though just with a quadratic, something that we could do without calculus, and we'll see how it lines up with this new technique.
Here's a function we should have a pretty good idea of how to draw already. Y equals x squared minus 6x plus 2. It's a parabola. It opens up. You could find its vertex with stuff that you learned in grade 11. But let's try this new technique of thinking about slope. So what I'm going to do here is I'm going to differentiate this function. So I have dy by dx is 2x minus 6. There's the slope anywhere. Now if I think about a parabola, the most important point on a parabola is right here, where the slope is 0. That's where the magic happens. That's where the vertex is. So what I'm going to do is I'm going to hunt down that x value. I'm going to substitute 0 for slope and see where that happens. So I'm going to have 6 is 2x, where x is 3. That's where there's a slope of 0. Slope of 0. And we call that kind of value a critical value, or a critical x value. Now you might have also noticed that that's the number that's going to zero out slope earlier on. Maybe you want to just factor this and call it 2 by x minus 3. you could see right away that the x value that will zero out this slope is going to be 3. Once we have that, we're not all done. We want to do a little bit of sign testing on this. And this is going to look a lot like your inequality work that you did in grade 11. So 3 is the most important x value in the life of this function. And what I want to find out is, what is y prime like before 3, like to the left of 3? So you can pick a number, any number that's smaller than 3, and plug it in y prime here, or the derivative. So if I put in 2, I'd get 2 times 2 minus 6 is negative 2. I'd get a negative number. You might say, well, what if you put in 0 instead of 2? You'll still get a negative number. If you put in negative 1,000,000 for x, you'll still get a negative number. For all the x values less than 3, the slope is going to be negative. And that tells you that y itself is decreasing right until it gets to 3. Now think about this parabola. Of course it's decreasing to begin with. Okay, now I'm going to test on this side. Let's put in a number that's bigger than 3. Maybe we'll put in 4. 2 times 4 minus 6. That's going to be positive 2, or a positive value. Or if I put in 1,000,000, it's still going to be positive. So what does this function do? It goes from decreasing to increasing. Let's draw that. Decreasing to increasing. And that means we must have a minimum at 3, and it'll have a corresponding y value. Now, if I want to find that y value of the minimum, I'm going to have to sub it in to the original here, where it says y equals. So to find the y value, it'll have to be 3 squared minus 6 times 3 plus 2. Let's see, what is that? 9 minus 18 is negative 9 plus 2 is negative 7. So this function is decreasing until it hits x is 3. Then it's increasing forevermore. When we found out the coordinates of that minimum point on it, it's 3, negative 7. Let's draw it. 3, negative 7 would be right here. I can easily find the y-intercept on this function. It's 2. Okay. And let's just follow the instructions. It decreases, and then it increases forevermore. Is that how we expected this function to look? Yeah, probably. Parabola that opens up. Could we have found the vertex a different way, say through negative b over 2a or through completing the square? Absolutely. But this calculus way is going to help us find max and min points for functions that aren't just parabolas, that are higher order polynomials or weirder functions than that. Let's take a second to look on Desmos just to make sure I'm not lying to you about the look of this function.
Yay! As expected, it looks like the parabola that we graphed.
If we want to be really clear about the intervals of decrease and increase on this function, it is decreasing for all x less than 3. It is increasing for all x greater than 3. And you can also write those in interval notation from negative infinity to 3 and from 3 all the way to infinity. Now, different textbooks will differ in whether they include the 3 in here. It's not a big deal either way.
So from our work on that parabola, we find out that smooth turning points are going to occur where you have a slope of 0, that's the condition 1 here, f prime of x equals 0, and f prime of x changes signs. So that means that you change from increasing to decreasing, or vice versa, on your original function. When we talk about max or min values, these are generically called extrema, or extreme values, and there are basically two types of them. There are absolute extrema, which are the biggest or smallest y values ever on the curve. So on that first curve you can see it's got some turning points, but only one of them takes you as low down as the function ever goes. That one on the right is the absolute minimum. And since that function goes up forever, it has no absolute maximum. The types that we're generally more interested in are local extrema. those are any of the turning points on a graph. And that's what we use the sine table, or we're using a number line to find for the first derivative. So you can see this second graph has 2 local maxes and 2 local mins, though it does go up and down forever in the end. In terms of a technique for finding max and min points, here's what we've got. So max and min points help us sketch curves, and critical values help us find maxes and min. For today, we're only going to focus on critical values where the derivative is 0. So that means where slope is 0 or where it's horizontal. And here's our technique for trying to sketch these curves. First of all, we'll differentiate. Then we'll find critical values on the first derivative. And then we will make the number line and perform a sign test around each of the critical values. So we're not subbing in the actual critical values themselves into the first derivative. We're subbing numbers that are greater than or less than those values. We interpret the meaning of a positive or negative slope, so figure out where it's increasing and decreasing. And then finally sketch. And we'll use the y-intercept too, because it's easy to find the y-intercept, especially on a polynomial.
Now let's put that technique to use on a function that is not just a parabola. So here we've got a cubic, negative x cubed plus 3x squared plus 5. We're going to find local extrema, so that means all the max and min values, and we're going to sketch. And since we're going to sketch, let's just take a second and find the y-intercept because it's so easy. If I put in 0 for x, I'd just be left with 5. The y-intercept of this function is 5. Where else does the magic happen on this function? Well, it happens where slope is 0. That's where we expect to maybe find a max or a min. So let's differentiate. The slope function is negative 3x squared plus 6x, and that 5 turns into a 0. I want to find out where the slope is 0. So I can actually set it to equal 0, but it's probably easier for me just to factor it and do it by inspection. I'm going to choose to take out negative 3x as a common factor, and that would leave us with x minus 2. Now what's going to zero out this whole slope function? The number 0 here, or the number 2 for this bracket. Those are our critical values. And just to be clear, they're numbers that would cause the slope to be 0. Or in other words, slope is 0 at these x values. So since they're the important points in the life of this curve, let's make one of these number lines. And what we're going to do is test around the points 0 and 2. And I'm going to be clear here that I'm plugging values into the derivative, and then I'm going to say what they mean on the original. So let's choose a number less than 0. Say we choose negative 1. That would be negative 3 times negative 1, okay, from here. And then negative 1 minus 2 would be times another negative 3. Now, I don't actually care what that number is. I care whether it's positive or negative, because that's what will tell me whether the original function is increasing or decreasing. So negative times a negative will give us a negative, which means to begin with, this function is decreasing. Now think about that. Does that make sense? If you have a cubic that is decreasing, it kind of has this type of look to it. Yeah, of course it's going to start by decreasing. If you had chosen negative 1,000,000 to put in here, you'd still get a negative. So that was a little scrap work that I did. I'm going to get rid of it. And I'm going to find out what's happening on this interval. If I put in, say, the number 1, which is probably the easiest number between 0 and 2, to put in here, I'd get negative 3 times 1 minus 2, which is negative 1. Oh my gosh, I'd get a positive. So this function would go from decreasing to increasing. Let me draw that down here. Oh my gosh. That means that there is a minimum at 0. and 0 something. I'll find the y value in a second. Okay? So lastly, I'm going to figure out what happens on the far right side of the curve. So if I put in 3 for x, I'd have negative 3 times 3 times 3 minus 2. Let's see, that'll be a negative times a positive would give us a negative, which means in the end the function decreases. And again, it kind of looks like this, so we're not surprised. So right here at 2, it changes from increase to decrease. Let me draw that. Ooh, that's a max at 2 something. And again, I'll get rid of this little scrap work. Before we go any further, notice that we didn't sub 0 into this, because we knew what would happen if we put 0 into this. It'll give us a slope of 0. We care about what happens on either side of these critical values. Now, if I want the y value at this min of 0, I'll go back to the original. Look, the original even says y equals. If you want a y value, go with that function that says y equals. So if I put in 0 here, I get 0 plus 3 times 0 plus 5. Oh, we kind of already knew this value. If I want to get the y value when x is 2, then I'm going to have to sub in to the original, so it'll be negative 2 cubed plus 3 times 2 squared plus 5. Let's see, that's negative 8 plus 12 is positive 4 plus 5 is 9. There we go. If I want to sketch this function, let me take those points and actually plot them. So 1, 2, 3, 4, 5. This point right here should be a min at 0, 5. And it's probably just a local min. If we don't specify, we assume we just mean local. The point 2, 9, here's 2, here's 9. There's a max. And then I look at my instructions. It says, to start with, you're decreasing until you hit that min. That kind of makes sense. That's how you make a minimum, is decrease towards it. And then you increase until x is 2, or until you hit that max. And then you decrease forevermore. Now, where exactly is that x-intercept? I don't know. We'd need some other fancy stuff, since this is not factorable, to find it. But it is going to be somewhere out there, bigger than an x value of 2. Let's check Desmos to make sure that our graph is okay.
So once again, it looks exactly like what we graphed. If I click on these points, we can find out min at 0, 5 and a max at 2, 9.
In our final example, I want to address one common mistake that comes up, or sort of assumption that comes up. And that is, once people find critical values, they often assume that they're going to be max or min values, but that is not necessarily the case. So critical values don't guarantee extreme values. We still have to make that number line or some sort of a sign table to test what's happening. Where is the curve increasing or is it decreasing? Just because it has a slope of 0 somewhere doesn't mean that it changes from increasing to decreasing. Let's check it out on this final example. So we have a quartic. It's just so easy to find the y-intercept that let's do it. The y-intercept is 2. Okay, let's differentiate. It's not hard to differentiate. dy by dx is going to be 12x cubed minus 24x squared. I can set that to equal 0 and then look for some of those critical values, or I can just factor it and do it by inspection, which is what I'd prefer to do. So 12x squared is a common factor here. I know there are 2 terms, but that doesn't necessarily mean it's a difference of squares. That would leave us with x, and would leave us with minus 2. And from that, we can learn that just like the last one, the critical values are going to be 0 from this, You can think of this as its own bracket, minus 0 and 2. And let's be clear about what we mean by those critical values again. These are x values where slope is 0. And no matter what else happens, that is still true. So let's test what's going on. We have to test around 0 and 2 on the number line, which is really just the x-axis. We care about what's going on with y prime. That's what we're subbing into. And then we interpret it in terms of what that means on the original function. So if I pick a number that's less than 0, say if I put in negative 1 into this derivative right here, I would have 12 by negative 1 squared by negative 1 minus 2, which is negative 3. Okay, 12 times negative 1 squared. Negative 1 squared is just 1. So this is 12 times 1 times negative 3. That is a negative value. And I don't really care what that negative value is. That means to start with, this function is decreasing. And again, you kind of know that about this quartic because it's going to have some shape sort of like this. I don't know what happens in the middle, but it's going to come from up top and then go back up top eventually. But what happens in the middle is the story we're trying to tell. All right, if I choose a number between 0 and 2 and put it into this derivative, say I choose the number 1. So that'll be 12 times 1 squared. And I think the more of these you do, the more you'll just do this in your head. Oh, that's another negative value. Oh. So there is not a max or a min here. It goes from decrease to decrease. But it goes from decrease to decrease by passing through a slope of 0. What does that look like? It looks like this. And we've seen those before. We might have called them saddles or hesitations, or really what they are horizontal inflections. But it's fine with me if you call it a hesitation. And where is that happening? It's happening at 0 something. Let's tell the rest of the story of the life of this polynomial before we go and find those y values. So if I put in something bigger than 2 into the derivative, say I put in 12 times 3 squared times 3 minus 2, which is 1. That's definitely a positive value. I don't care what it is. Now we're increasing. So we've gone from decreasing to increasing. And if I actually draw this, it's hard to botch whether it's a max or min. Decrease to increase. Hey-oh, it's a min. And that min occurs at 2 something. That's the life of the curve. Decrease, slope is 0 for a second, decrease some more. Then increase, and never change directions again. Let's see where the points are. If I put in 0 into the original function here, I'm going to get 2. So that is a horizontal inflection right here. At this point it goes decrease, horizontal, then decrease again. If I put in 2 into this, let's see what I get. 3 times 2 to the 4 minus 8 times 2 cubed plus 2. So what is that? That's 48 minus 64 plus 2. I'm going to get negative 14. And I can put that on my function too. At 2, negative 14, there's a min. Min 2, negative 14. Now I just have to connect it up. So decrease, horizontal for a second, but decrease again, down to this min. I'm trying to do this as smoothly as possible. And then increase forevermore. Let's check it out on Desmos and see if we're correct.
Once again, Desmos confirms the shape and the location of all those important points. And you can see that inflection where it really does go to a slope of 0 just momentarily and then continues to decrease. And at the bottom, it goes to a slope of 0 but changes from decrease to increase.
So now that we know it's correct from Desmos, we're ready to be able to do some of the practice questions. But one thing that might be nagging in the back of your mind is, why would we do all this stuff if we can just do it on Desmos? And one of the answers to that is that you never see the whole graph on a piece of graphing software. There's always the question of what's happening further to the left or further to the right or further up or down. With an analytic technique like this, you know that there is no other turning point that can possibly happen again because there is no other place where the slope is 0. So in that sense, you're kind of trumping the technology. But Desmos is an excellent tool for you to check your work, so please do that when you get down to the practice. Good luck.